Welcome everybody to Just Enough Math. I'm going to post the link to this sheet in our LinkedIn group. Thank you. So everyone will have access to the sheet and can play around with it, save your own copy, change it. It's basically a cloud-hosted Jupyter notebook. That's what this is called. So everything's in Python. And if you're having trouble accessing it, just let me know. And, I'll take care of it. Okay. So, just usual introduction. My name is Ahmed. I'm a software developer here, and this man is.
I'm Justin. I teach math at Lone Star College.
And our goal here is to give you just enough math, as the name implies, to help you with common development tasks. But we do hope that this is going to be broad enough to where other people can get something from it. Even though I've been developing software for quite a while, and Justin is actually quite good at math, it's his job, we're not necessarily experts in the set areas we explore. So definitely consider this a collaborative talk. If you have any questions, you kind of have any experiences you want to share, please chime in.
Yeah. So like for example, we're going to be presenting material about market research, but we're not exactly market researchers. Ahmed is closer than I am for sure.
Yeah,
and in fact, I'm not going to steal your thunder.
Well,
Yeah.
I've been working in market research for quite a few years, but we're also we're also being a bit speculative about the case study too. Kind of trying to extend it. So.
Yeah.
Cool. And opinions, any experience expressed here are not necessarily the opinions of our employers, etc. So, just the usual, yeah. Okay. So today we're going to talk about probabilities and distribution, and a little smidgen of statistics thrown in for good measure. So we're going to talk about what is a probability. What does probability mean? What is a distribution? What is weighting? And how we use these to try to model things, right? And also, if at any point I'm going too fast or you want me to repeat something or talk about something, please feel free to stop me. I definitely know, I have a tendency to go too fast sometimes. So just tell me, hey, and I'll be happy to slow down. Okay. So, and we're going to look at a case study. And this is a case study from my days in market research. And a case study is on something called reach, right? We've heard the ChatGPT having a little conversation about it. And the idea essentially is that some advertiser wants to create an advertising campaign. They want to put a bunch of ads in a bunch of different media at a bunch of different times. And they want to know, how many people would have seen at least one ad in this campaign, okay? Because that way it helps them plan where they're going to advertise. And so, this was a problem we faced in my previous role, or prior role rather. And so we have survey information and media habits from people, right? We get all this information, kind of like those telephone surveys we were talking about, and we know, what do you listen to, what websites have you visited, that sort of thing. And we have it all from a prior periods, and we even know how many people each respondent of the survey represents, right? What we call the weight. And so we wanted to figure out how could we model how effective an advertising campaign is going to be. And it had to be a model because no one really knew how the campaign would do. We had this older data, you didn't actually do the campaign yet, so we had to simulate it. And so we had to build a probability model to do it. So, and we're going to show you how what we're going to learn can help us build a model by extending the model we did. Justin's going to go really deep into that one. Okay? So that's just a case study to keep in mind as we start going through. This is what we're building up to. Kind of figuring out how many people we're going to reach with this advertising. Give us a simulation. So, probabilities. Okay, so probability of something is just a chance that it will occur, right? For example, I flip a coin, right? I may get heads, I may get tails. There's a probability for each outcome. And when we use probabilities, we have our probabilities lie between 0 and 1, okay? So a 0 means something will not happen. A 1 means it absolutely will happen. And then in between, like 0.5, gives us, the chance it'll happen. So if I flip a coin, assuming it's not a weighted, a fair coin, not weighted, the opposite of that, then I would assume a 0.5 probability for heads, 0.5 for tails. And normally, and a lot of times you're used to seeing percentages, that's just 100 times this probability. But normally we're just going to use a number between 0 and 1. Okay? So, now, when you get into probability, there are some useful things we can do with probability to figure out other probabilities. So if you have a probability of something happening, right? Then you can find out what the probability of this thing not happening is by just subtracting it from 1, right? So, you know, if you have a probability that something's going to happen, like the 0.1, and you want to know what's the probability it's not going to happen, 1 minus the 0.1, 0.9, okay? And then if you have several events, several outcomes, and they're all mutually exclusive, meaning one doesn't impact the other, you can figure out what the probability is of any of them happening by just adding up the probabilities, okay? So over here, you can see we're just basically adding them up, and here's just the summation, right? We usually use the summation notation for adding them. Cool. Questions so far? So very closely related to probabilities is the idea of a probability distribution, okay? So a probability distribution tells us what the probabilities are for every outcome of an event, okay? And we have a lot of different types of distributions we can use. I'm going to walk you through a few of them just to give you more intuition for what a distribution is. But different outcomes, different types of things obey different distributions. And so if we're looking to model something, we want to understand what is the distribution of this thing we're trying to model, okay? And then random numbers that we draw are going to be coming from this distribution. And modeling, again, is useful when we don't have information for something and we need to simulate it. And again, modeling is what we're going to do with our case study. So the first distribution that I think a lot of people may be familiar with is a uniform distribution. And this is just a distribution where the probability of any outcome is the same, okay? And if you've written any software, used any random numbers, used a random number generator, you probably use the uniform distribution even if you didn't realize it. So for example, here I'm just calling a uniform distribution, but if you're just calling like just a function called rand or random on your system, you know, whatever language you're using, it's almost definitely is using a uniform distribution. And all it does is just generates it. So I'm saying, hey, give me a random number between 1 and 7, right? Up to 1, just shy of 7, and just check and give me 10 of those. And just produce it in 10 random numbers, right? No big deal. Equal probability of getting any particular number. So far, so good? So the idea behind a uniform distribution, again, is that the probabilities of any given events, of any given outcome is going to be likely. So I've got here a little bit of code where I'm just calling a uniform distribution, pulling in some numbers, 10 of them, and then I'm plotting them, basically putting them in a bin. So they have these little intervals. So let's look at this graph right here. Now I said that I'm using a uniform distribution on this. But if you take a look, we have a whole bunch of numbers missing. Why isn't this uniform? Well, I mean, it is quantized, but is there something else that maybe looks a little bit suspicious as to why we're not getting Too many what? There are too many bins, or another way of looking at it is that the sample size is very small, right? So let's increase our sample size here. Hey. Now, you can see here we've got more, but it's still not uniform, right? Okay, let's increase the sample size more.
I'll be right back.
Sure. In fact, let's say I want 10,000. Okay, get it a little bit better. Let's try 100,000. Okay, what the heck, let's go for 1 million. Right? So important thing about the distributions. Whenever you have a distribution and you pull in some numbers from it, the more numbers you pull, the more you're going to start to see the shape of the distribution emerge, right? So in this case, we really had to go, and I was binning them, right? I was also binning them across 50 bins, right? And that was a good point, Kai. So here I had to go to about 1 million before we saw something that started to look like a uniform distribution, right? So that's one of the key things, that as you start to approach a sufficiently large number of samples, then you start to look like the distribution that you're aiming at. Does that make sense? Now, okay, so discrete uniform distribution. So discrete uniform distribution is just like a uniform distribution, except that it is discrete, meaning that there's a countable number of states, right? So if you go up to this previous distribution here, you saw that I said, give me a number between 1 and 7, and I got a 3.56, a 2.6, 1.78, right? But with a discrete one, in this case specifically, I'm going to go ahead and I'm going to say, hey, give me a number between 1 and 7 and make it an integer. And so I'm going to get 1, 2, 3, 4, 5, or 6, right? Discrete values. And in this case, and this sort of thing simulates, say, the roll of a die. Assuming you're rolling a die, Vegas die, not Dungeons and Dragons, right? 6-sided die. And oh, there you go. And Peter even brought his dice. Wow, you're prepared. But are those fair dice or are they loaded? Right? So each face, the probability of getting any particular roll at each face should be equally likely, right? And of course, it is a small number of states, or a countable number of states. So in this case, we've got, again, uniform distribution. And so again, here I have a sample size of 10, and I'm also showing the frequencies of everyone. I have 2, and I just say, hey, give me 10 random ones out of this uniform distribution. And it's like, okay, here's 2 1s, 2 2s, 1 3, and so on. And again, you can see here that this doesn't look uniform because, of course, we have a very small sample size. And that's actually another thing, too. So always remember, when you start thinking of sample size, the more you pull out, and this is important for statistics, right? The closer you can get to representing the type of phenomena of interest. So again, we'll go to 1,000, and it starts to look a little bit better. And in this case, we have a smaller number of bins, too, so that's also helping us. In fact, we have 1 bin for every state. Okay? And so what you see here also is that your numbers, right? So there's still differences in your frequencies, right? You have 1683 for 1, 1662 for 2. So there's still differences, but because the differences are small with respect to the sample size, right? Or rather, with small with respect to the brackets, you start to see a closer convergence to that. So when people start talking about things like the probability of something in the long run, it's not because you run into a string of luck. It's just that after a certain number of time, large enough sample, those differences, those fluctuations tend to smooth it out because they're much smaller in terms of proportion. Questions? Okay, so now let's talk about the normal distribution. Okay. Do you have a question, Peter? Okay. So the normal distribution is where we get into some more interesting distributions because the uniform is a little bit, a little dull. So normal distribution is one where your probability is not going to be equal, okay? You're actually going to have a sort of clustering effect, not even sort of, a clustering effect. And you have a lot of phenomena that aren't uniform. So take, for example, heights, okay? And I just Googled this, so whether or not this information is correct, I don't know, but that's the extent of my research, so So adult male heights in the US. Supposedly, the mean, right, your average adult male height, and I use the symbol mu for mean, okay, is 5.75 feet. Then you have this number called the standard deviation, right, which tells you how widely spread out from the mean the values are. And in this case, the standard deviation is 0.2333 feet. So essentially, it's telling me something about how these heights in the US are distributed. So let's say, for example, I wanted to use a uniform distribution to figure out, get some random heights. I would think, okay, what's the minimum height of a person, of a guy in the US? Maybe 2.5 feet, right? Like the smallest person, right? And maybe the tallest guy is like maybe 8.5 feet, right? And I may just be revealing my ignorance of biology, but let's just say that that's the range, right? And I'm like, okay, well give me like, say 1,000 random heights in that. It's gonna give me these heights with equal probability, right? So I'm equally likely to get, say, 3 foot tall guys as I am, say, 5'2", right? Which is nonsense, right? We know that most of the heights are going to be clustered around this center, which is going to be around 5+ feet. and even though you have some very short and very tall people, they're going to be very rare, right? And that's what the normal distribution is. So when we look at the shape and the normal distribution, and again, all I'm doing here is I'm just giving the sample size, mean, standard deviation. And Python has a lot of I use the NumPy library, which has a ton of math goodness. So I just say, hey, give me a normal distribution, right? That's the extent of my math. Just to actually show you how to calculate some of this fun stuff. But I'm like, yeah, this is how I calculate it. I call it library. And so I'm like, hey, give me that. And of course, we see that these numbers, this graph looks like crap, pardon my French. And we all know why, right? Why does it look like crud? Small sample size, right? So let's crank it up a little bit. Okay. Let's go for, well, I won't say go for broke, but let's try this. Okay, now we're starting to see something, right? And what the heck, let's go for a million. Okay, much nicer. So what we're seeing here is the classic shape of, or the shape of a normal distribution, okay? Also, thank you, made it myself. Also known as the bell curve. Yes, sir.
This is real data or it's just fabricated data?
Well, no, I'm just using the mean and the standard deviation,
Okay.
and then I'm basically drawing, yeah. So what I'm
Using
doing,
a random number generator.
Yeah.
essentially right. So over here, so what I'm doing here is I'm saying, hey, give me a bunch of random numbers with this mean out of a normal distribution, with this mean and this standard deviation. And so that's all I'm doing is I'm pulling in these random numbers according to that distribution.
Okay.
So yeah, having surveyed a bunch of people in the U.S. and saw that their height should roughly fall in this pattern, but this is all just random numbers drawn from the distribution because we're talking about simulation in this talk. Yeah. I wish I did the research. I'd love to interview a million people and ask them their heights.
If I can just make a
Sure.
side point, now that we talked about uniform and normal distribution, right? For which one is the the mean of the distribution? Have you talked about that yet?
The mean?
The expected value.
No, I figured I'd leave the expected value up to you, but I did talk about the mean. Essentially your center points.
Right. So for which distribution is the mean of the distribution more meaningful? The normal, right? Because it's all, like here's the mean, right? Everything's, all the probability is clumped in and around the mean, right? With a uniform distribution, you can make the interval as long as you want. You could have like an interval of like a million units long, right? And have a uniform distribution on it. And like the data could be anything from 0 to 1,000,000.
Yeah.
Like all with equal probability. Now the mean of that is 500,000, but who cares? What does that tell you about like where the data is going to fall in the future? It's equally likely to be 1,000,000 or 0.
Yeah. And I replotted it, so literally you could see the mean 5.75 is right smack in the middle. Right? Yeah. And so and your data tends to be symmetric about the mean, right? So it tends to be distributed roughly equally around this.
And the standard deviation, of course, is what is a good, at least one way to kind of measure like how meaningful the mean is, right? Because the standard deviation tells you how well clustered. If it's low, it's a relative term, but it's clustered more tightly around the mean. If it's not, it's like could be really far from the mean, and that's much less useful.
Yeah. Like take a look at these scales. You've got a 5 here, you've got about a 6.5 here, right? Let's go ahead and change our standard deviation to say 0.8, right? So we're increasing our standard deviation. And so when we hit this, watch the scales. You'll see how the scales have gotten much broader. Now you're going all the way out from 3 feet to over 8 feet because you've got a broader standard deviation. And that controls the spread around about your mean. And same, of course, if your standard deviation, and I should have just used this guy, right? Is super low, right? Super low standard deviation is going to give you, say, 0.1, right? Something ridiculous. And you'll see a super low standard deviation, how tightly packed your data is.
Yeah.
Right?
So, yeah, like you could have a normal distribution also. Now that you've done this, right? With a high standard deviation, right? And yeah, that does impact like how meaningful the mean is, right? Or how useful the mean is. But it's kind of a different story than the uniform distribution, right? Because what you see here is you have these what we call tails, right? Where it's clearly the outliers. You know, there's some sense of like an outlier here, right? Like things that are super rare, which is not so uniform distribution.
That makes sense, everybody? Yeah. And an outlier, of course, is a value out at the edge, but I think it's normally defined as what? Was it 3 standard deviations away from the mean?
Yeah, something like that.
Yeah? Okay, cool. Oh, thank you. Definitely speak up, please. Participate, don't be shy. So other examples of normally distributed data, right? So test scores, and I'm sure as a professor, Jesse can verify.
Actually, what was the significance of the 3 standard deviations?
I don't know that there's this real.
You know, you
well,
just never see it. You almost never see it. Oh, it's just a really, really rare.
Yeah, that's like the rarest. Anything past that is like a critical point.
I see.
So you're trying to avoid that area past the 3.
There's specific numbers, like once you pass, for a normal distribution, once you get past 3 standard deviations, the probability of that happening is no. It's, you know, it's small, so like 3%. Was it, Brian?
Yeah, I was gonna tie up like there's this concept within quality control called Lean Six Sigma.
Mhm.
It's actually related to within 6 deviations,
Yeah.
standard deviations, because I think after the 3 standard deviation is like 0.00003% probable happening. So they always try to keep all the good quality to be within 3 standard deviations.
Yeah. Yeah.
And it's arbitrary. I used to see for outliers and stuff.
Sure.
Yeah.
And
Yeah.
it probably comes down to your use case, right?
Yeah.
So, in physics, they use 6 sigma. I know for like that when they do experiments at the super colliders, they insist. I think, or is it 5 sigma? I can't remember. Like the Higgs boson experiment, I think the detection of the Higgs boson, they insisted on 5 sigma. So 5, they had to be like that. The result had. That, I guess that's a measure of the statistical significance, right? It had to be, you know, what is it? Yeah, like that, the result that they got had to be outside of 5 standard deviations, assuming like the other hypothesis, the null hypothesis.
Very unlikely to be reached by chance.
Yeah,
That's what we're really trying to do.
that's what what it can be used to quantify.
Yeah.
So how likely a result is to be gotten observed by chance.
Yeah. And if you notice that, and that's why we call it 6 sigma, right? Because you notice this symbol right here is sigma for standard deviation, right? So yeah.
Go on.
Okay. So yeah. So like 6 sigma would be like 6 times, for example, that. So kind of see where the sigma comes from. Cool. That's really good. Any questions or comments or? Okay. So now we're going to get to the binomial distribution. This is going to be really what we're going to use for the media model, right? So we've seen uniform, discrete and continuous, we've seen normal. So now let's look at the binomial distribution. So the binomial distribution is a kind of distribution that you're going to use when you want to figure out what are the different probabilities of success over an experiment that's repeated a certain number of times. Okay? So,
And binary outcome.
a binary outcome, yes, thank you. Success or failure, binary outcome. So in this case, so essentially we're talking, so for example, let's say we go to our die, our little 6-sided die, right? And you want to ask, hey, I want to roll this die a certain number of times, let's say 15, okay? 15 times. That's going to be the number of tries, okay? So we'll keep this number in mind. And if I get a 5 or a 6, I want to consider it a success, okay? A successful outcome. If I get anything else, a 1 through 4, I'm going to consider it a failure. And so I'm interested in knowing, hey, if I do this trial 15 times, what's the probability that I'm going to have, say, no successes, 1 success, 2 successes, right? Through these 15 runs. So the first thing we need to do is we need to figure out what is the probability of success. Remember, our die is 6-sided, right? So each side has a probability of 1/6 of success. Right? Hey, what is it? So I want to know though if we're going to have a 5 or a 6. Right? So you remember from previously, if I want to know about the probability of any of a set of mutually exclusive events happening, I add their probabilities, right? So the probability of a 5 is a 1 out of 6. Probability of a 6 is a 1 out of 6. Uniform distribution, right? Equal probabilities. So I just add up. 1 plus 6 plus 1 plus 6 equals 1/3, right, when you reduce it. And it's roughly 0.333. I'm rounding it because we don't need to be terribly precise in our case. So like, okay, so I got a probability of success of about 0.333, and I have 15 trials. So let's see what kind of successes I'm going to get. So first, just to kind of get a quick idea of the code, and again, code's fairly straightforward. I'm basically just calling this function. This function is the binomial distribution function inside Python. All the stuff's built in. I think Justin will show you how to calculate this stuff manually, but you know, I use library functions, so someone else wrote it, I'm going to use it. And you just give it a number of trials and your probability of success per trial. So I'm giving it a 15 and a 0.333. And we're going to tweak those parameters in a bit. Then the rest of this, I'm just basically graphing it all. But essentially, once I get this distribution, remember, distribution tells you the probabilities of all of the outcomes. I can then query the distribution by calling the PMF function, or method. And that just stands for probability mass function. And it just tells me, hey, what's the probability at 0 successes, 1 success, 2 success, okay? So I can query it for every level of success just by calling this function. And I'm just calling them for all the values and plotting them. So, we'll go ahead and hit it. And you can see here what this looks like. So 15 trials, 0.333 chance of success. And down at the bottom, you see the number of successes, and on the x-axis, and the y-axis, you see the probability. So the probability of not getting a 5 or a 6 on any of the 15 rolls is really low. Not quite 0, but pretty close, right? Probability of getting 1 success, a little higher, and so on. What's the highest probability? Well, I'm sorry, the highest probability that we get in our trials.
What outcome has the highest probability?
What outcome has the highest probability? Sorry, Mr. Grammar. Huh?
5.
Yeah, 5, right? Yeah. Justin's good about making sure that I don't get sloppy with terminology. It irritates me, but he's good at it. So, right, so this is 5, right? And you can see here that we've got a probability, that's the highest probability, it's above 0.2. And you can see here that again, as you start to go for more and more successes, you tend to drop, right? Pretty much accords with intuition. So we see here the full probability distribution, right, for this experiment. And we know at every given point what the probability of the successes, of that number of successes are.
What's the mean of this distribution?
What's the mean of this distribution?
5.
Yeah.
I would say around 6 or 7.
Well, it's around close to 4 and 5. So 4.5.
Well, I guess it's
Would be
exactly 5. But yeah, that's because the formula for the mean is NP. So and it's or what's the number of trials times the probability of success is the formula.
So that's 15 trials times 0.3333, but that's 1/3, so that's 15 over 3. 15 divided by 3 is
5.
You just need more tries to get it
to get it closer.
to look cleaner.
I mean, we can definitely increase, right? We can definitely increase our trials, right? We can say 150. Let's see.
15 billion.
Well, I'm a little bit careful, but we can see here and so this starts, yeah. So you start to kind of see, you know, again, the more refined, but you got so many more trials here that you can see probability of any given success tends to be a little fairly low. What happens if I increase the probability of success per trial? Like, what if I make it more likely? Maybe I want to roll a 2, 3, 4, 5, or 6. What do you think happens to this?
The standard deviation decreases.
Okay. You're saying the standard deviation decreases? Okay. Anybody else want to guess? So
This is from what it's at now.
Oh, no, it gets skinnier.
it's skinnier?
Yeah.
Yeah, it gets skinnier.
Yeah.
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 So okay, let's check it out.
Yes.
So you can see here that, so you see how of course, we're now kind of centered more over our larger numbers because we have a higher probability of success, right? So the graph's kind of shifted right here. And you can see again, our highest number of success is, our highest probability is going to be at 12 successful outcomes out of our trials, right? And of course, if we lower this to something, what do you think? Yeah, this happens, right? And again, you see, we don't have, we're generally going to lose a lot of our successes, and we're going to shift much more towards the left, right? So your probability of success, of course, is going to have a big impact on that. And then this will just kind of give you a more kind of refined, finer grained view.
What's the mean of this distribution? What's the mean of this distribution? It's not 0, but close, right? So definitely 0 is the most likely outcome, which is the mode, right? The most likely outcome is called the mode, right? So mean, again, it's number of trials times probability, so what's the mean? Or I should say the expected value, right?
Brian had his hand up.
So I guess, would it be accurate to say that the closer it is to 50%, the more it looks like a standard, normal distribution?
So you're saying the closer this is to 50%, the more it looks like a normal distribution?
Yes.
Well, let's take a look and see here. Because what we have, this does tend to take on a more classical one, and that's because at this point it's going to be symmetric about the mean, right? Which is one of the properties of a normal distribution. Am I correct, Justin, or did I put my foot in my mouth?
Yeah, normal distribution is symmetric about the mean, that's for sure. That's a property. So it's bad. Yeah, it makes it a little bit. I think when p is closer to 0.5, it looks a little better. But the result.
It would be weird if you flip the coin
If I recall,
and one side's more.
the limit of, as the number of trials increases,
Yeah,
the
it's the
distribution
one
becomes more normal.
That's just the number of trials is the key parameter, not the p. But probably the p it's nicer to have it closer to 0.5.
Yeah.
I think,
But if it's very close to 0, then you don't have space on this side, right?
yeah, but it'll still approach. It'll just be very, very tall and
It'll
skinny.
be tall and narrow.
Yeah, just be very tall and skinny.
Oh, okay.
I want to say that it would approach,
See there?
it would get there a little faster, the more moderate value of p, but I don't know.
I see it, yeah.
Yeah, kind of see what's happening here?
Yeah,
So-
yeah, so you can see that. So it's a normal distribution, but it's just very squished.
Yeah, and as Kai was saying, right, you get a
Yeah.
squishy distribution. I should coin that.
That's why just instead of, if you just have a loaded coin that's always bad sense, right? That's 100%, it's just gonna be a straight line.
Yeah.
Yeah,
It's a skinny line, that's it.
Yeah, so
It's
that's
100%. Or it's 0%, it's always
So-
just a line.
what's the standard deviation of that?
0.
Right? So so something that has 0 standard deviations, it's not random, right?
That'd be a degenerate normal distribution.
It is. It is.
I like using the word degenerate. I keep on trying to
Yes.
ask him these questions because it's mathematicians like this.
It's actually a line.
Huh?
It is a.
It appears more often than you would think.
Is there something on the definition of standard deviation, the normal distribution saying that the standard deviation cannot be 0?
I don't think so. No, I mean, not technically, no. But
Just physically, you can't have negative error, plus or minus. It's always plus or minus some margin of error when you're measuring something, right? And the only way and the only way to get the
there's no
error.
negative standard
Because
deviation.
then technically, a line is also a normal
Here's your
distribution.
graph.
Yeah. And there's a graph, right? It's like one, yeah. Yeah, so a line, you could say a line is also a normal distribution.
A line?
You're like this.
Well, I just said standard deviation is 0 just so I'm pocket. So, and that's what
Okay, yeah,
So,
right.
you know,
I gave you something.
yeah. Cool.
Yeah. That's degenerate.
Good questions. Cool. Is there any other questions so far? Okay. So, So we're about to get into the case study. So I want to give you a quick outline of how this binomial distribution applies to this question of how many people do you reach with an advertising campaign, right? So again, if you remember, you have advertisers and they're putting these ads on these different time spots on these different media, right? So maybe they put some ads on some website, attach some to another video, maybe put some on a radio station during an average quarter-hour window, say 8 to 8:15 a.m., and so on. So they have like all these ads, they kind of, put them out there. And so we have, again, survey information on different people. So we get like a sample of 1,500, well, 1,400 more like, people, say in the Houston area, but we do it nationally, right? Who basically tell us everything they do, everything they eat, their ages, what they listen to, all that stuff. So we know their media habits, we know their demographics, we know that, and we even have weights for them, so we know how many people in the population each one represents, right? We call that the weights. And so we're like, okay, we now have this respondent, we know what media this respondent pays attention to, what media they consume. And we've got this advertiser who says, hey, what if I place all these ads, okay? How many people are going to see it? And so we're able to simulate this with a binomial distribution because we look at the respondents and we look at all of the ads on the media the respondent pays attention to. Okay? So every single ad during the media time the respondent pays attention to is a potential to actually see the ad. Okay, there's a probability of actually seeing the ad. So those ads are the number of trials. We treat that as the number of trials. Then,
Number of ads is the number of trials.
yeah, the number of ads across the media the respondent pays attention to. Right, that's the number of trials.
The ads are trials.
Yes, the ads are trials. And then every respondent also has this probability of actually viewing any given ad, right? And this is something we could simulate or estimate. Maybe we go ahead and look at the demographics. You're like, okay, they're fairly young, they're into extreme sports. I don't know, they probably have low attention spans, right? Not necessarily fair. We think, yeah, you're probably not going to stick around. You're going to go to the bathroom during a commercial, right? Something else we figure you have a higher chance of sticking around, that sort of thing. But it's something we could try to estimate based on information we already have. So you have a lot of lifestyle and demo information. And so we have a probability of actually seeing any given ad, and we've got the number of ads. So now we can actually build a binomial distribution and know, okay, what is the probability you're going to see 0 ads, 1 ad, 2 ads, up until the total number of ads. So far, so good. Now, since we're interested in knowing if a person sees at least 1 ad, we're interested in knowing, hey, what's the probability you saw 1 ad or 2 ad or 3 ads all the way up to however many number of ads, right? Which means we add those probabilities. So,
Add with 2 Ds, right?
add with 2 Ds the probabilities for watching an ad with 1 D.
Okay.
Yes. So for example, we're just going to assume you have these media and time spots called A, B, C, and D. Yes, sir.
So are we saying that we're assuming there's 0 for people that didn't see any ads? Or, so like everybody saw an ad, so it's always 1 at least?
No,
Not necessarily.
It could be 0.
Yeah, it could be 0.
Yeah.
Yeah.
In fact, that's probably the most likely thing.
Okay.
Yeah, because it's very possible that if you have a respondent who didn't consume media A, B, C, or D, they saw 0 ads.
So no ads is the possibility?
Oh yes,
Yeah.
absolutely.
Okay.
And it's probably the most likely possibility because any given ad campaign, I would imagine most people probably don't see it unless you're really got deep pockets and you're saturated,
No,
right?
you just said every ad is a trial, but it can be not.
Yeah.
But it can be no ad.
Right. Just like rolling a die, you could have no successes,
Gotcha.
right? Yeah. That's a good question. Yeah. So it's very, very possible and even likely that the average person wouldn't see a single ad. So in this case, we got a media, right? So media time spot A gets 10 ads, B gets 8 ads, C gets 3 ads, D gets 2 ads. Okay? We're going to assume that's their ad campaign. And we have a respondent, and they only consume media A, B, and D, right? So they're not going to see anything that's put on C. Okay? So they have a possibility of seeing, right, 20 ads because there's 10 on A, 8 on B, and 2 on D. Right? So 20, so in this particular case, for this particular respondent, 20 is the number of trials. Okay? Now, again, through the information we have in simulation, we figure this probability, this respondent has a 0.2 probability of seeing an ad. And that's probably fairly high, right? I'm just making these numbers up as an example. Okay? And now we just want to know what's the probability that they're going to see at least one ad. Okay, questions before I continue? So over here, I'm going to show you the code. So again, all I'm doing is I'm calling a binomial distribution, right? Number of spots this particular respondent could see, or number of ads. We also call them spots. Or I should have called them spots. That way wouldn't be confusion between ad and ad. 20.2 probability. And I get the binomial distribution. And then because I want to know if they saw one ad, two ads, and so on, remember probability of any of a series of events happening are mutually exclusive, you just add them. And so here I'm just adding all of these, all these probabilities from 1 up until the number of ads, but not 0, because at least you saw at least one ad. And so in this case, with 20 ads and a 0.2 probability, there's a 0.988 chance that the respondent saw at least one ad. Okay? Now, of course, if this number goes down, right, we would expect, again, to be a lower probability, right, 0.18. And if you got deep pockets, you can go for a really nice aggressive ad campaign, right? You can get very good numbers, which again is pretty much what we would expect. Okay? So now, I'm going to put this back to here so we have this original number. Now, we went ahead and just added all these probabilities, but there's actually a bit of a shortcut we could have had, right? Remember, you can never see less than 0 ads. As much as many of us would like to, you can't see a negative number of ads, right? There's some ads I'd love to see, but that just doesn't happen. So we have no less than 0 ads. So asking about the probability that you see 1 or more ads is the same as asking the probability that you did not see 0 ads. Does that make sense? Because if you didn't see 0 ads, then you saw 1 or more. So you could save yourself a little bit of summation and probably speed things up a bit, or speed things up a bit, not probably, just by saying, you know what? I'm just going to subtract the probability of just 0 ads from 1. Because remember, 1 minus the probability is the probability of that thing not happening. Okay? And if we do that, we see here that we get a number that's very close. It's a little bit off here, but that's rounding. Okay? And that's more than accurate enough for my purposes. Okay? Questions so far? Now, and so of course we want to say, well, okay, cool, so I know what the probability is that any given respondent is going to see an ad. But how many people saw it, right? You want to know how many people did you reach trying to advertise Save Houston? Well, this is where we get into weights. Because any given respondent has a weight associated with them. This is something that they would actually calculate, figure out, and provide as part of the data. So I have some respondents say she's between 45 and 50, she makes 150K a year, we have all this demographic information. We're like, okay, well, we know that she, based on all of her demographic information, represents, say, 5,000 people in Houston, right? So like, okay, well, if I have this probability, and I know what the weight is, how many people this person represents, I can just multiply the 2 and come up with an estimate for how many people represented by this respondent saw an ad. Does that make sense? And so in this case, for example, all I have here is like, hey, here we are with our 20 ads, right? And again, 0.2 probability, and we're going to go ahead and say this person represents 5,000 people. And so here we can estimate that, okay, well, you would have reached 42 people from this one person, right? Or at least based on this respondent. And so then what you would do is you would just simply sum it up, right? Go, okay, for our next respondent, we have this probability of seeing an ad, right? Maybe they're super impatient, right? And there's very few media they like, so they probably only saw, one media, but they represent a lot of people, 50,000, and we're like, okay, well in their case, we got 4780 out of them. And you would go that for every respondent, sum them all up, and then you would get all of the people you would have reached in your ad campaign, a simulation of it, an estimate of it, in that market. Does that make sense? Okay. Now, Justin's going to take you on a deeper dive on this because I did simplify some things here, right? I went ahead and assumed that that one person has the same probability of seeing an ad regardless of what medium they're on. Some people pay more attention to certain media than others, right? Some media you kind of turn on when you're vacuuming, right? So definitely assuming just the same probability is a very simplistic assumption, but it makes the example easy to talk about. He'll make it more realistic and go into detail. I didn't get into details on projected for the entire population. I kind of talked you through it, right? And I also used the built-in binomial distribution function because, hey, it's there and, but you can actually see how it's actually calculated, right? And so so Justin takes over from here with a detailed treatment, and he's going to go into more details and kind of dig deeper into the math. Cool?
Okay.
Go for it, sir.
You got it?
Yeah, sure, absolutely.
Okay, so yeah, first of all, I'm not a market researcher. I just sort of was piddling around with this based on reading a paper that was written by someone at Google a while back. Maybe, can we go all the way back down and show the Go all the way down.
Oh, you want to see the further reading?
Yeah, so it's this, the optimal mix of TV and online ads to maximize reach. So it's just kind of like
Yeah.
goofing around basically, and I kind of got the idea of like what they were doing. I stole some of their notation, like the FIJ. Yeah, I use FIJ. They use FIT for I and TV, and T probably stands for TV. I think. But anyway, at some point I stopped reading and just kind of like was like, oh, I think I can do this. So I just kept going. So I may have like plagiarized their model whole cloth. I'm not sure. I'm not like so. It's just FYI, it's there. I'm not taking like credit for this. They do weighting and stuff. I didn't do weighting, although I had weighting in mind. Anyway, okay. So just wanted to direct everybody to that. That was the inspiration.
When you get access to this, you'll have access, of course, to all the links, and you can play around and change the examples yourself, save your own copies. Okay, so again, I'll provide access in the LinkedIn group. I'll send you access if you can't access the LinkedIn group. Please let me know, but you'll get all of this. Okay, we always provide all of those sheets for everybody to play around with and experiment. Okay, so we want to go back.
So here goes the math teacher's perspective on market research. Now that we've got the market researcher's perspective on that. So I meant to flesh these out a little bit more, but I didn't get a chance, so sorry about that. I'm going to try to do it afterwards, but which is fine because you could all see my edits later. It's just going to update and boom, it's going to be right there. So this is my basic expression. If you could kind of zoom in on that a bit.
Oh, you want to
Do that?
Sure.
You're good. Sure. Yeah, that's good. So okay. So I'm going to start off with this. Now I just want to make it clear, entirely clear what this means because I know it looks like a mess. So first of all, n. If you scroll up a bit, we can see n actually. So n is the size of our target audience. Okay, so we're kind of drilling down to the individual level here. We're treating each individual individually. And then L is just the number of placements. Now, within each placement, right, there's some number of ads associated. So just as an example, you can think of a placement as being a segment of time on a TV or radio station, something like that. And then like within that segment of time, you buy a number of ad placements, or a number of ad spots, right? And so we have those two parameters, and then of course, there's the number of ads that exist in each placement, right? Next, I want to make clear what Fij is. F sub I and j. So this is a whole, an array of parameters basically, where the first index I is specific to the audience member, right? So the ith audience member, and j is the placement, so the jth placement. So an f is the number of ads seen by consumer I from placement j, right? So if you have, just think of me as consumer I, right? Then I will potentially be exposed to all the placements, and if you sum those up, right? Sum up the number of times that I caught an ad from one of those placements, right? That's the total number of times I've been exposed to that ad.
And just real quick, did you kind of explain, so place by placement, and this is something I glossed over, so that's on me, right? It means, right, an ad at a particular media at a particular small amount of time.
Right, yeah.
Right. Did you say that? I had a brain fart, sorry.
Right,
Yes.
would this be the equivalent of impressions when we talk about Google Analytics?
They're similar to impressions. In fact, you can think of, because some people will calculate impressions, they'll actually calculate them differently based on different media, but some will calculate impressions as like the number of ads they'll see, and they won't like scale it back for repetition. So if you have like 500 people seeing the same ad 10 times, they'll call it 5,000 impressions rather than reach. And in fact, some people will calculate reach from impressions. So there is, I believe, a close relationship between the two. But they will calculate it a little bit differently depending on a medium, but it is closely related to it, absolutely. In some models, it might actually be the same thing. It's just they do it a little bit differently for ads. Does that make sense?
Yeah.
Based on media. Okay. Sorry about the interruption.
No, no. Glad you said that. So, and also just for clarity, the inspiration here is that we're talking about placements, you know, in that situation that I mentioned earlier, where placements being those things like quarter hours or half hours or hours or whatever, right? So I guess we talk about quarter hours.
And we like quarter hours because we like it to be granular, because if somebody's watching a particular, say, medium, right, and you kind of sample it over the whole hour, they might have stepped in or out, whatever, but if the narrower your sample, like quarter hour, the more a chance that an ad there is something they would have seen, right?
Yeah.
But yeah.
So we really, you know, like up here with the definition of L, we could say, instead of number of placements, we could say number of quarter hours or something like
For
that.
example, yeah. That would not be a bad way, yeah.
So I'm going to go with that interpretation for that. Okay, so Fij being defined this way, right? The number of ads seen by consumer eye from placement J. If I write Fij, and then I sum, right? I freeze I, so I just want to talk about the ith customer. So imagine I'm the ith customer or whoever, right? And then I sum over J. So J of course enumerates the placements, right? So we've got the first placement all the way up to the 11th placement, right? And this is the number of ads seen by me or whoever on the during the jth placement or the jth quarter hour, right? And this is the sum of all those. So this is the sum total of all the ads that I've seen, right? This is the total ads seen or heard by a consumer. Maybe I should say audience member.
Audience or even respondents.
Responded, if we're talking about a survey, right?
Yeah.
It's responded.
But you can treat all those terms as interchangeable, right? Consumer, respondent, audience member.
This is like you, your A, right? Respondent, I, right? Okay. All right. So then I just want to breaking down that first expression completely, right? So this is the summation that you see here appearing as a subscript of the number 1. We're going to get to the 1 in a minute, but first let's understand this, right? So to say that this sum, I'm just going to copy it, is greater than 0 means what? Respondent I saw an ad, at least one ad, right? This means respondent I saw at least one ad. So, and what does that mean? That means, in short, we're using a term for that, right? That's our definition that we've been using. I don't know if we emphasize that well enough, but that's our definition of having been reached.
Quarter hour?
That they saw one ad. No, for summing over all quarter hours. So it's like, just imagine maybe it's a day, right? This whole campaign happens in one day, right? So we buy like in a day there's like what 90 quarter hours, so we buy like 20 of them. And, you know, so we sum over all 20 quarter hours, and within each quarter hour, we might have 3 ads or 5 ads, or that's kind of 5 ads seems like pushing it, but like maybe 2 ads or whatever. So this is the sum total
So over the whole survey, at least one ad.
of the whole survey.
Like, or you're saying over the whole day, or over the whole.
For the whole day, yeah. The ad, if the campaign is running for a day, then yeah. Yeah, so this is the probability, or this is the number of ads that person I has seen in the course of that day. Or the course of the entire campaign, whatever the campaign is, right? So this, again, so that it's positive means it's not 0. So they saw at least one ad. And so that's our definition of having been reached. So this further means consumer I was successfully reached. Okay.
Did you have a question, Brian? I think I saw a
Yeah,
hand go up.
so this specific formula, would it be on the case where you have, so L is how many like placements?
How many quarter hours? Yeah.
And so this would be a case where every single person receives the same placement, right?
Mm-hmm.
Because like, I know
Yeah,
like,
it's just, I mean, it's not an internet-based.
yeah, because I know like with internet, like,
situation.
especially like Google marketing stuff, like you might have like impressions in this case would be more like an individual level rather than.
Yeah. So if we get to it, we may not have time, but if we get to it, I do have an example that is based around YouTube ads, and it uses exactly the same framework. Sorry, not it's supposed to be a combination of TV and YouTube ads, and so those would be considered like 2 components of the same campaign, modeled differently, but you can use this framework potentially for that as well. Although it's a little bit more rigid. Probably there's better frameworks than this, but
Yeah, I'm guessing this is beneficial. It's like let's say on TV, you don't really know for sure if somebody saw the ad, right? Or is there a way?
right. But so the assumption is that we have sort of a group of respondents that we have like reasonably good data about, so we know the probability that they're watching a certain channel during a certain quarter hour, right? And then then you know, from there, it's just you might need a little bit better data to know like what the probability is that they would catch an ad, given that they were watching, right? But we don't get into the weeds on that. We just assume that we've got some historical data that to allow us to essentially allow us to estimate what their probability, the probability of success, right, in the context of a binomial distribution, right?
Is that why you said, is that why you defined it as reach, so that you can do a binomial distribution?
Is that the reason we define reach this way? So that we can do a binomial distribution?
Did you say that?
No, not necessarily. You could use other distributions.
Okay, I just,
I mean, but it fits. Yeah, it fits. But there, yeah, it's not like you can't just use any old distribution. Binomial is definitely a good fit for this.
I don't even know what
I do want to also comment on something so Brian did bring up. So, there also have been, and different companies have done this, based on different devices to try to measure when someone's actually watching, right? So we may have heard of the Nielsen set-top boxes. I didn't know that's still a thing, right? But Nielsen, the TV ratings, and they used set-top boxes so they could actually know if you were in front of your TV and on what channel during what time. A company called Arbitron, at the time the biggest radio ratings company in the US, I don't know if they still are, they actually had a device called the PPM, the Portable People Meter, and they would actually incentivize people to carry it with them, and so if they were walking by a radio station, they would record it, and they would know, oh, this person was exposed to this radio station around this time slot. And of course you mentioned analytics, right? You got a lot of folks trying to figure out what side you're
I think
at.
a good modern way to look at it is like Google, like through cookies and stuff, you're able to tell if an ad is on screen. Like if you're scrolling, you'll be able to tell, oh, this ad appeared on the screen or not. And then of course if you click on it.
Right.
Just because it's on the screen doesn't mean it's being watched.
Well, right. That's the other thing too, right? That's why sometimes you hear the term exposed to an ad, which just because you don't really know necessarily if you watched it or not, but the ad played while you were physically there, even if not mentally there. But it does bring up a good point that a lot of these simulations also are because, if we had good measurements, or if we had all these measurements, we wouldn't need the simulations, right? We just would wait. That's something we need to do is wait. But because we don't always have these simulations, or rather don't always have these measurements, we have these models, right? But absolutely.
Although at least like with digital ads, you have the idea of a click, whereas on a TV you wouldn't be able to click.
Right.
Right. So.
Yeah, so you can at least measure some kind of engagement, like, oh hey, unless they clicked on it by accident, you're like, there was some interest. They were, unless their hand twitched, right? They were paying attention, right? Yeah, absolutely. You have more ways because it's an interactive medium. Absolutely. Yeah.
I imagine Elon Musk's neural link will help make inroads into that in the future to determine what you're actually looking at, where your attention lies.
Let's see what the adoption is of it.
I thought we were still very far.
I think you could probably get good data on that. Just like beta, at least like which way your eyes, like, I think, yeah, because there's already technology to interpret like, like the input from, like the impulses that the brain receives from the eyes and stuff like that.
Yeah, I can say that. But like, you need like a whole measurement across your brain, right? Because I know Neuralink, they're supposedly like they implant it in a specific place.
Yeah.
So you could get data about your visuals.
Right. Yeah.
Right. It's supposed to be like visual cortex, I think, is supposedly the only
Well, not
thing.
with the base model, right? They'll upsell you.
The upside.
Yeah, if you want to know what this person's seeing. Yes.
Yeah. Wow. Okay. Well, all right.
Yeah, most of your brain is dedicated to vision.
Yeah, like visual cortex, right? Or is it most of it?
No, the reason yes.
Okay.
Not just vision, but the entire brain is mostly dedicated to vision.
Okay.
It's mostly dedicated to what?
Visual processing.
I don't know, I leave YouTube playing in my sleep, so.
Yeah, that's right.
Well, that's the thing. How they account for so think about like how Netflix has ads now on their cheapest model, right? I imagine advertisers use some kind of framework like this to determine what ads to put on Netflix. But now with the age of like smartphones, yeah, you can have this stuff playing on your TV, but are you actually like looking at it, or are you looking at your phone? So you might have been exposed, like you might be on, you might be physically in front of your TV set, actually looking at it. I imagine that has a whole nother layer of complications.
Yeah. And in fact, that could be something where that whole probability of like seeing an ad, you could adjust that. Like, okay, well, let's drop that number by half because you're on your smartphone all the time and you're probably not, right? So you can like cram a lot of sort of behavioral information to that one number. But yeah, it's a very good point. You may continue, sir.
Questions?
Yeah.
Okay, so, well, have I convinced everyone that this sum being greater than 0 means that respondent I has seen at least one ad, in other words, they've been reached? Okay. So what about that 1, right? So that's what's sometimes called an indicator, right? So if E is an event, right? Maybe I just call it then we put the name of the event in the subscript, right? So again, this is an event, right? This is a random thing. Okay, it's a random number, right? Sorry, this is a random number. Together with the statement that it's bigger than 0, that's a random event. That's either going to happen or not going to happen, right? So if it happens, that 1 with that subscript, that's subscripted by that event, is going to register a 1. Right, if the event happens. And what do you think it's going to register if not? A 0, right? Right. Okay. Now we get to level up to the next sum. What am I summing over? Summing over the people, right? So this is just really a big sum of zeros and ones. What it is. The big sum is nothing but, it's just a big sum of zeros and ones. It's either 0 if the person didn't see any ads, and it's 1 if they saw at least 1 ad. That's it. So I told you it wasn't going to be so bad, right? Math is a language, you just got to learn it. That's it. So, and then of course, why am I dividing by n? I guess I don't really have to divide by n, but dividing by n does what? It makes it like a fraction of the population. So the respondent set, right? The audience, because n is the audience size. So it's just so the output of this is going to be, it could be 50%, or it's going to be a number between 0 to 1, some fraction of the audience, right? And without dividing by n, it's just the total number of people that were reached. That's it, right? Okay, so then, so this is a random thing. So like when you run the ad campaign, some fraction of the audience is going to get reached. There's no, it's not a deterministic process. It's a random process. You do it more than one time, you get different outcomes, right? So in order to get a good middle of the road estimate for reach, we take what's called the expected value, which is akin to an average. It's conceptually linked to the idea of an average, right? So the expected value we already talked about. It's kind of the middle of the distribution. At least if your distribution is nice and well behaved, it's meaningful, right? So the expected value is also what we've kind of colloquially referred to as the mean. Okay, so if taking expected values on the first line, right, results in this. So if I take an e here and here, right, this is what I get. Because if I put an e here, I can push it through the sum. So that's a sort of a result from probability theory, which is not a big deal, right? If basically you have this, if you have two random quantities, right? Think of like the number of successes in a binomial trial or something like that, right? Say x is that, and then you've got some other random quantity, right? And then each of these have their individual means or expected values, but you want to sum them together and think of that as a random quantity. Well, it's as simple as just summing up two means, right? That's all it is, right? It's called linearity. Oh, thanks. Yeah, I sound funny.
No, when I talk a lot, I get parched, and I just assume that you're like me because I'm narcissistic.
This only works if X and Y are independent.
Not true.
Okay.
Works no matter what.
Okay.
Good question. The associated idea for variance works if X and Y are independent.
Okay.
Yeah. So variance, if you know, is the square of standard deviation. So it does work. Yeah, you have if you want to take the variance of a sum, it would be the sum of the variance if you have independence. I'm about to talk about independence. Okay. So yeah, all this quickly generalizes to if you have the expected value of the sum of random quantities, that's the same thing as the sum of the expected values, right? So you just take that expected value symbol, you just push it through the sum like that, right? If you've taken calculus, you know this already too. So this is called linearity in calculus of the integral, right? Take an integral, f of x plus g of x, right? That's the same thing as the integral of f of x plus the integral of g of x dx for the part of calculus folks. All right, so it's the same idea. In fact, it's literally the same idea if you look closely enough. Okay, so that's the first step. Another thing, I won't write it on the board, but since this is a constant, since 1 over n is a constant, so it's a non-random quantity, it can just come right outside. That the E just goes right through it. So that 1 over n doesn't cause any problems. We push the E through. Now I've got 1 over n times the sum of these expected values. All right. Now, to understand the next line, there's not, I mean, it would take a while to go through it. But the expected value of an indicator of an event, or I'll call it event E. Wait, that's too many E's.
Yeah, too many E's.
Z. Okay. If Z is an event, right, and one sub Z is its indicator, then the expected value actually comes out to be the probability of the event itself. That's the theorem. It's from probability theory. So you can find it in most textbooks. So that's what happens in the next line. So you see that the E was transformed into a P, where the event, again, is that event what? That consumer I was reached, right? So here we have now what is this? This is the probability that consumer I was reached. See, now we're talking, because we can start modeling that, right? So we can use the binomial distribution, for example, to start writing down these probabilities, right? But first, I want to use the trick that Ahmed alluded to earlier, or more than alluded to, explained very well, which is that the probability of something being positive, if the let me back up. For this, what are the possible values for this sum? Right? What's the smallest value that sum could be? Right? In the case that what customer I is not reached, what is that sum? 0, right? So it could be 0, it could be 1, it could be some other positive number, right? So what's the opposite of this happening? Right, the probability that this sum is greater than 0. If that doesn't happen, then what happened? Right, and mathematically, what is that? The fact that this sum is actually equal to 0, right? So Ahmed mentioned this property, right? That if you have an event, the probability that E does not happen, right, is equal to 1 minus the probability of E, right? Probability that E does happen, right? So that's the next line, right? And that's actually just to make things. You could kind of stop here, but this is going to make things a little bit easier or it's going to make the expressions nicer to work. Okay. So at this point, it's really just algebra. This sum gets pushed through. Now I have a difference, right? This sum gets pushed here onto the 1 and onto this probability here. So the sum of n ones is how much? It's n, right? So the 1 over n is going to cancel with the n and leave me with a 1. And then once this gets pushed over here to these probabilities, I'm going to have a sum of these probabilities. Okay. So this is 1 minus 1 over n. Sum of the probabilities that the ith customers, or the ith respondents won't be reached. Okay. Finally, you want to say, okay, how can that sum be 0? Literally, how can the sum of only things that could be 0 or greater, how could that possibly be 0? Only if they're all equal to 0, right? So the only way that this sum is equal to 0 is if Fij are all 0. Okay? So that's what this says. If you're familiar with this logical quantifier, it's read as for all. So for all j, Fij is 0. Okay. Why do we want to do that? Because now we want to assume that the quarter hours or the placements. I shouldn't say campaigns here. I should say placements. That's a typo. Or actually the lack of editing. But if you want to assume independence. Or if you assume independence, then you can convert this probability into a product of probabilities. I'm not sure how familiar this big pi symbol is, but it just means multiply them all. So just multiply over j, and then this means for sum over I, right? And so I should talk about a little bit about independence to make sure that seems reasonable, right? So things are independent if they can't impact each other, okay? The best interpretation to me is that, okay, you have event A and event B. They're independent if, like, once you know that event A happened, that tells you nothing about event B, right? Event B happening or not happening has nothing to do with A happening or not happening, right? Does that make sense? So if you've seen conditional probability before, this is the probability that A happens given that you know B has happened. And so that may be different from the probability of A, right? But if it's not, then we say that the events are independent. So if this is the case, right, the probability that A, given that we know B happened, is the same as just simply the probability that A happened, right? This is the textbook definition of independence. Now the fallout from that is that if you want to know the probability that both A and B happened, and that's as simple as taking the probability of A and multiplying by the probability of B. Okay, so that's why I say if you assume independence of the placements, right, statistical independence of the placements, then you can just turn this thing that says that, you know, this is just a long list of, you know, things that happened, you know, all at once, or all in the same campaign, or whatever, right? So it's just, you just multiply all the probabilities together of them individually if you have independence. And that's nice because it makes, you know, it makes the math a lot nicer, basically. So as you can imagine, you know, under some circumstances you could consider the placements independent and some you couldn't, right? So what is that? What do y'all think? Does that, what are some situations where independence could be violated? Like say, in this scenario where we're talking about quarter hours on a TV station. Like when could those be independent or not independent? What do y'all think? Any ideas?
You watch an ad and you're so disgusted, you turn off the TV and you don't watch it anymore.
That's, yeah, so if you happen to be running a very disgusting ad, I guess, like, that could mess up your independence assumption, yeah. So, like people, yeah, so, or offensive, right? So, like, turn off the TV, I don't want to see that.
Maybe you're so lazy you don't change the channel. So like if you watch one ad, you're gonna watch another one.
Yeah, totally. If I turned on the TV that day, right, and like all the quarter hours are like associated, right? It's like if you saw one, you saw them all. That's a perfectly good example, yeah.
If you're watching TV, you're probably not listening to it.
That's true. So if we get into different media or different station, you could have the potential for overlapping, right? So if like if you're watching one station, you can't be watching the other, right? So that would violate. If the 2 quarter hours are at the same time but on different stations, then they are not independent. Because if you saw one, you definitely didn't see the other. I like to, generally speaking, I think that if 2 quarter hours are closer together, they might be associated. I kind of feel like that.
Yeah.
Yeah, because like, you know, like, I mean, if you're just watching a 30-minute sitcom, then that's 2 quarter hours. If you watch the first one, you're much more likely to watch the second one, right? Yeah. But if one's like, you know, 2 totally unrelated shows, perhaps, you know, then those would be more, well, no, that's actually bad. That's not right. Yeah, but if they're just, you know, further apart, you know, yeah, you just, you know, I don't think they would have too much bearing on each other, right? So.
But closer together is going to make it more likely you're going to be watching the second quarter hour, both because of programs, but also just kind of spill over
Yeah.
Like you're driving, for example, you just have your radio on, and
Yeah.
your commute could be 30, 45 minutes, people still listen to the radio, you know, so I hear,
So I mean, I tend to think that there's no obvious reason why, you know, two ads that are separated pretty well in time would be closely correlated. So, but I could be wrong, so I could totally be wrong. But anyway, so assume there's some sort of situation where you have independence, and let's move on. That's basically how it goes in most like writing of research papers. Either we're going to assume independence. Let's move on. So.
So you did
All right.
where do we go?
Down. So okay, we have an application of ad sequences placed in multiple quarter hours. Okay, you know, same stuff as before. N individuals, L quarter hours. Into each quarter hour, we place a sequence of ads. Okay, great. So for each person, right, we're going to have, every time a quarter hour comes along, that's going to be a binomial sequence that is modeled by a binomial distribution. So I'm a person, I'm watching the quarter hour from 8 to 8:15. There's 3 ads run, that's 3 trials. You know, each one has a probability of success, meaning there's a probability that I'll see it, right? Okay, so that's it. Keep scroll a bit. Okay, so every Fij is going to be binomial distribution where, okay, this notation, this xj is the notation I'm choosing for the number of ads that are purchased in the jth quarter hour. Okay, so xj is the number of ads that will run during the jth quarter hour. And Pij is just the binomial probability of success for person I for that quarter hour. So that such granular probabilities they need to be estimated to make this model run. So you have to know the probability that a person is going to see an ad for every given person in every given quarter hour for this to work. Okay. All right. So. This expression here is derived directly from the binomial distribution. So I guess there's really no need to go into it. The binomial distribution is, of course, on Wikipedia. You can find that the probability that a binomial random variable is equal to 0 is 1 minus the probability of success raised to the power equal to the number of tries. Okay? So that's the formula that I'm going to sort of insert into the general formula that we had above, right? So if you remember that formula, it looks exactly like this, except that before I simply had the probability that Fij equals 0 here, but now I'm going to replace that with a concrete formula from the binomial distribution. So the probability of seeing 0 ads is this expression here. All right, so let's keep going. So once you do that, you can just start computing the reach at that point, right? So assuming you have these parameters, estimated for each quarter hour in each individual, you just plug them in, and of course we might be interested in the values of X, right? So as a marketing firm, you might be interested in, well, how many ads should I place in these quarter hours? So that's a problem. We're not going to get into that, but that's certainly a variable of interest, right? How many ads do I buy within each quarter hour? Maybe I buy 0 ads. Maybe I buy 5. I don't know. But anyway, this expression can now be thought of as a function of those choices, right? So we can compute. So I wrote up this code to just basically implement this function. So can you go down a bit? Sure. So we're going to generate. We're going to use this function to generate some concrete values for this model. Let's scoot down a bit. And so here are some values that we chose, or I chose for. So we're talking about 1,000 individuals, 4 quarter hours. I, generated X, as a sequence of random integers, that represent the choices of ad placements, right? And then P is just I used a random uniform generator to generate probabilities of success between 0 and 0.1, and called my expected reach function on X and P. Okay?
So you're using a uniform distribution to test this.
I am. Disregard this text, maybe. Keep going.
Okay.
Keep going.
Nobody saw this.
Oh wait. No, what happened to my picture?
Oh, maybe. Well, let's see.
Oh, shoot. Yeah. Don't do that. Yeah. Okay. Okay.
That was
So,
interesting.
yes, that's fine. So what these are just, so because we had, hold on, 1, 2, 3, 4, 5. Why is there 5? Can you scroll up a bit? Sure. Oh, so that was, yeah. So I had L equals 5, right? So that's the number of placements. So each of these curves represents sort of the reach that you get for each placement. So in isolation, like if you allocated all your ads on that one placement. So this is as a function of X, this is, since there are 5 variables, this is like a function of 5 variables, so you can't really like draw a plot of it. So just kind of like drew cross sections of it essentially. So you see based on the various probabilities associated with the individual audience members and their proclivities to watch certain quarter hours or not. We see that this placement, it gets you sort of the worst, right? Sort of the worst reach, or increase in reach. Sorry, I should explain what's on the x-axis. On the x-axis, you have sort of the number of ads placed, right? And the y-axis, you have reach. Sorry, I should have labeled those. So this is so you see a pretty shallow increase in reach from this purple this purple line, indicating that for that particular quarter hour you don't reach. The number of ads doesn't translate into a great reach compared with the others. So these are sort of ordered in worst to best. So this could be like your reach curve for prime time spot or something like that. So we should change the ad max up there to like 100 or so.
You want to see the shallow.
So let's get a better picture of this. So it's not feasible to place. If we're talking about quarter hours, right? It's not really feasible to place 100 ads. So this is just kind of like, you could interpret it to be in a situation where it is feasible to place 100 ads or something like that, or as a proof of concept, because it's a proof that what we're doing actually makes sense, right? These are exactly the types of curves that you would expect the quantity of reach to follow, right? Yeah. Up here, again, reach, the way I've modeled it is between 0 and 1. So for this particular placement, you see that as you increase your number of ads from 0 up to 100, you're kind of asymptoting out towards 1. If you go even further out, you'll see that.
Crank it up.
You want to crank it up?
Yeah.
Crank up the reach?
Yeah.
3 is good.
Okay.
So that's what you see. Like as you increase the number of ads, you're eventually going to reach, the entire audience, right? But of course, that's not feasible. It's much more commonplace that you only reach, a few percentage of the audience, and this can be used for that.
Because there's going to be a cost per ad, and as you see, you're getting diminishing returns. And so at a certain point, it's just not worth paying the money to get that extra, tiny percentage bump, right?
Yeah. So I think that's, pretty much, like I said, there's an example following this that incorporates a YouTube campaign and stuff like that. You can just leave it there. So just to kind of run through it, basically in this situation, we're not talking about, quarter hours. We're just talking about, hey, I've got a TV campaign and I've got a YouTube campaign. And so those are my two independent ad, prongs of my campaign, and I can derive binomial models in the same way, Well, actually, the way it's derived for TV is very similar because of the similarity with what we just talked about. But for YouTube, you take a different approach. If you could scroll down a bit. So YouTube, it's a similar. It still uses the binomial distribution, but there's a different variable of interest, which is this M0, which is it's the fraction of the YouTube inventory that you purchase. Okay. So, anyhow, so I won't go into all that. We're pretty much, we're getting late. So, that's about,
Do you
so
want
that's the
to show
extent
any of
pretty
these
much.
graphs or no?
Huh?
You want to show any of these graphs or no?
You can run that, yeah. So this, maybe, well, okay. So yeah, I plotted it. Yeah, Ahmed will like this one, right?
Yeah, I don't
Ahmed
like
will
my
like
graphs.
Ahmed don't like 3D plots.
I'm gonna hate 3D plots.
Ahmed visual cortex need upgrade.
Oh!
Elon Musk.
Wow.
No, that's a pretty bad plot.
It's
I
like-
care for you. Anyway, so but again, like, okay, this is like a reach curve, like where you have like two variables, right? So it's not very interesting. I mean, we all need an upgrade to our visual cortex because none of us can visualize more than 3 dimensions. So so this is like two variables. It's just I plotted this just to show that it's that same like it starts off like kind of like it reaches increasing, but then after a while it just kind of flattens out. So that's all. Okay, so anyone want to ask anything or questions, comments? Thanks for listening. I hope you got a feel for what you can do with math. You kind of put your mind to it. I always tell my students when am I ever going to use this? And I always say, I don't know. Like, it's up to you. Like if you're looking for a math problem, I guarantee you can find one. But if you're not looking, you're definitely not going to find one.
You have a question, Kyle?
So what's the optimal ratio between the TV and?
Oh, and YouTube, you mean?
Yeah.
Well, I can tell you the optimal ratio. If you remember from the nonlinear constraint optimization, we had a simpler reach model that we used optimization to try to maximize. So, because remember, you're not just going to be looking at the ratio. And actually, Justin did have a whole thing where he had constraint optimization, and I was like, as much as I love it, that's going to be a lot for this talk. Let me see how long we are right now. But generally, the idea is going to be this, because you're going to want to try to get the most that you can, while also like basically minimizing your ad budget, right? Or at the very least, get however much you can within an ad budget. So the thing is, there's an additional constraint you want to keep in mind, and that's going to be the budget, right? Very high-performing media are usually going to cost you more, and some media are going to have a very small audience, but they're going to like grow a lot faster, right? And that was kind of like something from nonlinear optimization one. So the idea is that you have to take into account what the cost is going to be, and then you can figure out like what your optimal blend is, because it can definitely vary based on what your ad budget is, and then what you can afford based on the media you can choose from. Does that make sense? So yeah, so it is a pretty nuanced question. That's the one where you use nonlinear optimization to like solve something like this.
Yeah. Can you show the bad thing?
The bad thing?
Yeah, this thing. So, yeah, in the context of of optimization, right? This can be a little more informative, right? Because you think of your budget constraint as basically a line going through this plane down here, and then it has an image up here in the curve. So what you do, you optimize the curve, like over that cross section of this curve, right? So that's what your budget constraint would create, like a cross section of this, right? And then you find the maximum value along the curve on that cross section. Right. So.
Highest point.
Yeah. So you maximize your reach subject to your budget constraint.
Yeah. And it actually gets a little bit more nuanced too, because we didn't talk about another concept they like to balance called frequency, which is the average number of times a person saw an ad, right? So sometimes people will care about, or not sometimes, a lot of times they'll care not just how many people did we reach, but what's the average number of times each person saw an ad? Because the idea is that the more times you see an ad, hopefully the more it sticks. But if you see it too many times, maybe there's going to be some backlash, right? So some will trade a lower reach for a bit of a higher frequency under the assumption that reaching a whole bunch of people ain't gonna help if they're gonna forget about me that quickly. So in addition, you may also want to throw in a constraint on the frequency, right? So an additional constraint would be like, hey, I want an average frequency of say 3. But yeah, if you go back to the nonlinear sheets, and that's something that's something you'll find. That's something you'll find in the over on the LinkedIn group. Is it nonlinear? That's PCA. But I I can share it out to people. It's also in the LinkedIn group. We actually use a simplified reach model to kind of show how you could do that optimization, but we only use optimization with a constraint of budget. But yeah, throw in a constraint of frequency, and then maximize your reach subject to those 2 constraints. And that's going to be a little bit more like what a lot of advertisers are trying to do. But we were kind of like, that's also going to be a bit much to throw in there. Although the frequency level is kind of interesting, especially with binomial trials, because you get to see, what's the probability of being exposed at a certain level, and you can probably use that. That'd be an interesting application for frequency. But that's, yeah. Does that make sense? Or did I just kind of go off and ramble a little bit? A little both?
I guess.
Any?
Go ahead.
Oh, any other questions? Cool. Yeah. So again, cool. So I guess we're done here. I mean, for your hangout and chat.
One more time.
What?
Plug ourselves one more time.
Oh, plug ourselves.
Yeah. We meet.
Oh yes.
Wednesday every month.
First Wednesday every month.
First Wednesday every month here.
Yep. And yeah, trying to start our talks around 6:30. And pretty much yeah. So definitely by all means. And we're also open to suggestions for a topic.
Yes.
So if there's a particular topic that you're interested in like us talking about, let us know. We may have to research it depending on what it is, but we're definitely interested in feedback and see maybe if it's something we can present. Okay.
Yeah. Feel free to. Anyone have anything off the top of their head?
Yeah.
Do you have a plan to do something, cover the mathematics of cryptography?
Cryptography?
Ooh.
No.
I don't know enough about that to suggest anything in particular, but
Yeah.
the big prime numbers, that's all I can say.
Yeah.
Like different ways of finding
Yeah.
primes and their performance profiles, but
I don't
I'm
know.
most interested in their search.
huh?
Math, not really math.
That's not really math.
But
yeah, I don't
social
think there's
engineering
much.
is such an Actually, there's math involved in that. Like math.
I mean, yeah, because about the only math. I mean, there's also math involved in like calculating like your hash, like you're calculating your hash. Again, I don't know if it's like terribly sophisticated math, but it's going to be mainly. I mean, most of it will just be about why having those really big primes is fairly secure, and then I guess you could try to talk about why quantum computers would theoretically pose a threat to that. But then you get to quantum, it got pretty deep because then you want to talk about sort of position and how that would impact your calculations and so on. So potentially, I don't know if there's enough to really make it me, but I mean, something we can definitely at least think about.
Yeah. Do some.
No, like just talk about hardware.
Talk
Not the math, like the algorithms mostly are secure. Just talk about like RAM hammering and other ways to like keep the hardware.
I mean,
Like if you go to a specialized website and all it does is keeps writing to the RAM, like hammering it, eventually there's a chance it's gonna flip a bit in your hardware. It has nothing to do with the algorithm. It just flips a random bit, and then hopefully that bit is like a special no. Oh, I'm sorry. Maybe I'm talking over here.
I mean, you're talking over my head. You are. You are. Don't worry. You absolutely. But we can chat a little bit about it and see if there's something that at least we feel confident enough to give you something interesting on.
Maybe something like how quantum computers work, and why they can handle that problem, right? So that's the danger. So like quantum computers can handle that problem of breaking cryptography because of the way they work.
Yeah.
Like quantum computers are not like they're not like a catch-all can do any computation faster than a standard computer. But they're really good at certain things, and that's one of them.
Yeah.
But incidentally, there is quantum. There's like a protocol already written for like when quantum computers, if and when they take over, like so like there's already security protocols that have been put in place for that. So it's not like this arms race that I don't know if it used to be or ever was, but there was that conception that it was like arms race. Whoever gets the first quantum computer, they're gonna rule the world. It's like the one of the rings from Lord of the Rings or something. So, but I don't think that's the case. It's my understanding. It's just like everybody knows how to deal with it once it happens.
So the apocalypse in 2024 might not happen.
That could be independent event. Could not be impacted by that. No way. I don't know. But what, is it supposed to be in 2024 because of quantum computing? Or is it just because 2024 is like a multiple of 12 and last apocalypse was supposed to be in 2012?
We've got some politicians saying COVID didn't scare the public enough. The next is going to be cyber.
Oh, I see the next thing.
They calculated the reach of COVID-19.
We were exposed to COVID-19 at least once.
They're saying the cyber collapse of the bank
I could actually use my logo for that.
will be the only thing that scares the public enough.
Yeah.
The probability of
Submitting
contracting,
to,
right? That's going to be definitely a function of age.
They're calling it rules.
Yeah.
That'll impact the probability. Well,
How many events were you?
yeah.
Yeah, probability of contracting it, right?
Yeah.
And then how many events were you at? Although, yeah, of course you want to scale up by the possibility of COVID. Was that those events? Yeah, you probably did like sort of COVID reach model. Yeah. Anyway, that's another good one there.
Would y'all do I don't know what to call it, an episode, a meeting or something about, that involves, electronics, counting, like different ways.
Oh,
of
sure,
counting?
yeah.
I know that's not too,
That's a good idea, actually.
just
I
related
like
to
that.
probability.
Combinatorics.
Yeah, cause like, yeah, that could come up. I could see in some coding tasks. I guess. I mean, I'm not a developer.
I don't know about coding, but I know specifically, well, not specifically, but when I think it was, well, yeah, it was in probability courses. It usually comes at the beginning of probability courses.
Yeah.
Because you have to know
Yeah.
how to count the number of
Of
events.
ways that an event can happen.
Right. Yeah.
Yes.
And I remember that initially being like pretty confusing.
Yeah, combinations, permutations, and everything in between and around that. Yeah. So yeah, they're all applications of like the multiplication principle, where it's like you have a task and you divide it up into subtasks, and there's the number of ways that you can do each subtask. If you know that, then you just multiply them all together, and that's the way of doing the number of ways you can do the whole task.
The binomial, I remember the binomial theorem came out of that.
Yeah, binomial
Like,
distribution
sort of-
uses that.
And she's K.
And she's
Yeah. That's exactly what, the coefficients of the binomial theorem, the coefficients of the binomial theorem are exactly combinations, like in that sense, they're like the number of ways certain events can happen.
And that's super, like, knowing how to count things.
Yeah,
Given-
it's tricky.
Yeah, it's not as straightforward.
Yeah.
But like the, what is it? Yeah, I can't think of a good example.
I could give you, well, I mean, I don't want to hold everybody up, but yeah, I could definitely think of stuff to talk about for that. Yeah. And that would be kind of fun because it would be interactive, we could all try it and present our solutions and stuff.
It's fairly useful for testing too.